All right, it's recorded. Everything you say can and will be held against you. No, that's something different. Sorry. All right, guys, let's go with it here. Let me move this a little over here. So welcome to the last day of school this year. She whiz. Kind of fun. We're going to hopefully make sure that Kate doesn't freeze to death before she leaves. Well, that's one way to keep warm. Go for it. Preparing for the pajama races. We should do that, pajama races. All right, guys, let's go for it here. So we're going to take a slight detour in 3.4. We're going to go take a look at some application questions of derivatives. Once we do that, let me actually even check the next pieces here. Then we're going to jump to, I think we should be, yeah, then we should do trig functions here. So we take a small little break and with learning this stuff, and we're going to go into applications. So let's take a look at outline wise what applications we're going to look at real quickly here. We're going to take a look at some physics applications and this whole concept of position. And tell me if I'm writing too small here. Velocity and acceleration. So physics stuff. We're going to take a look at biology as well. Biology stuff and population growth, whether it's bacteria or growth of cities and human population here, but this whole concept of population growth. And then how about some business applications or economics? So notice that calculus, it just permeates everything.
That's because math is the best, and it's better for all applications.
That's a good opinion, and an opinion I share as well. And so it's just so cool how that all works out. And so they're like statistics, right? There's a non-calculus based statistics, and there's also calculus based statistics. And so there's calculus based physics and non-calculus based physics, just because you get to see so much more. And so you get to see change that you don't normally do. And so that's a cool little thing. Okay, with that.
Word say after economics?
Say again a little louder.
What does the word say after economics?
Oh, marginal. Sorry, marginal functions. Actually, I should say marginal functions. All right, and where did Eli go?
I'm fixing the heater.
Okay.
I'm still listening.
Okay, no problem. Just making sure you guys don't freeze to death over there. That's all. Okay, let's go with it here. So let's go with let's think things through here as we do it here. So I'm gonna give you a line, and you guys tell me if you agree or disagree with each line. Okay. So first things first is let me think I can put most of it here. So amount of change in a calculus sort of way, amount of change that we have. Tell me if you guys agree or disagree with this statement here. So if I'm looking at amount of change, I'm looking at this right here. And tell me if that's true. So if you're looking at a y-axis, right, just a quick example maybe, right, you have this one, which is f of a. And let's say this is a right here. And then we add h to it right here. So whatever this a plus h is going to be, this would be f of a plus h. And then really the amount of change is going to be this little piece right here. Right? It's the y, it's the difference in the y values technically, right? Okay, so amount of change is that. So next is the average. So if I know that one, I can give us the average rate of change as well. That's pretty easy to give because that's just going to be the same exact formula that we had before. Except we're going to, hey, let's use, let's use slope formula, right? That would be slope formula in terms of functions. So simplified version would just be f of a plus h minus f of a divided by h. Are we good there? So there's your average rate of change. It's the change that we had before divided by time. Cool. Okay, we good there. Is that the average rate of change? Everybody agreed? Okay, so then the next little piece here. Tell me if you agree or not. Oh, so that's the average rate of change. Instantaneous rate of change, which is what calculus is all about here. Instantaneous rate of change. And that one's going to be our limit function here. That's the derivative, right? So instantaneous rate of change is going to be the limit as h goes to 0 of, that's what calculus is based upon right over here. That's cool. And then here's where we get into a little bit of a fudge room. This is where like, hey, you know what? Kind of, sort of, kind of. Here's what we got. So if that is all true, then now let's start a reasoning process here. So for very, no chicken scratch here. For very small values of a, of h, dot, dot, dot. And when do we define small? Totally relative. But here it is. The derivative of f at a would be kind of approximately to the average rate of change. This is when, like, if you swallow this pill sort of thing, like if you swallow this, if you agree with this statement, then we have some application questions. So this is not exact figures. This is not an equal sign. This is approximations. There's a little error involved in the process. But this whole piece of, hey, you know what? I can figure out this and it'll be approximately true. This should be f of a right over here. That's the only, this should be f of a. And these should be squiggly lines because you were looking at approximations, not equal signs. Okay, are we good there? Okay, so let's do this here. How about let's multiply both sides by h. And then let's add f of a to both sides. So, bunk, multiply by h. So I got a multiplier here. Look at that. We're just messing with formulas now. And then let's add oh, I'm already adding in my mind here already here. No, should be adding a little bit later. And then let's add f of a over here. So eventually it looks like, let me do it both ways here. F of a plus h multiplying the derivative of a gets me this right here. And I'm going to just turn it around because I like the stuff that I'm solved for on the left-hand side. So final formula, here it is. F of a plus h is equal to f of a plus h multiplying the derivative of f at a. There's my formula. That's the one I want. And notice I slowly changed it to an equal sign, right? It's still an approximation. we should still keep it as approximations because no, it's not equal signs here. It's just, it's close, but not true. There's a little error. Okay, so they say a picture is worth 1,000 words. So let's do a little picture of this stuff. What are we actually even doing? What are we looking at? What are we trying to comprehend? We're trying to comprehend a quick way to look at small itsy bitsy changes so we don't have to take the derivative and we don't have to take everything else. Or sometimes actually you don't even know what the derivative is, or you don't even know what the function is. You can't even take a derivative. So this is just a quick, short sort of way to look at some changes. All right. Are we good there? Let me give you guys the graph to it here. And with this, hopefully it will make a little more sense here. So here's my little function. It's going to go like this. My point that I'm looking at is going to be, I think we can do it like that. Yeah. And I'm turning my computer around so I can draw a tangent line. So tangent line comes in like this, touches it just barely, so barely at one spot and keeps on going. Okay, so let's jam. So this guy is going to be our A value. That's what we're looking at. So this is A comma F of A as a point. And what we're trying to do is we're trying to estimate F of A plus H. We're trying to estimate the value right here, even though it's going down. Let's say it's like right here. This will be A plus H. This would be F of A plus H. So notice our equation that we wrote it in terms of F of A plus H. What we just did, that little formula we just made, we made that little dot down here. So notice this formula is, if we kind of think about it, this is your tangent line formula from before. This is your slope times your length. So this times, I do want to write it the other way here. Let's see, this is, right, I guess we could write it like this. This would be kind of fun to do, plus F of A. If you can kind of think about it, this is mx plus b all over again right here. Right, it's your slope. It's your x value coming across. It's actually, the h is on the other side. So it's h is the x. There's your slope. And it's this little line right here. So notice there's a little gap right here. There's a gap change, and that little extra little gap between them, this is your error. So that's why we can't put an equal sign. We're going to have to put an approximation. So it's like, you know what, it's kind of like almost there. It's an approximation to it. It's close. And it's not to give us precise answers. It's to give us approximations. Now the question is this: with population growth, do you count every single person in the city? Do you know the exact value of every single person traveling or not traveling the city? No. We make approximations, right? We say like, hey, there's about 45,000 people in SLO, right? So that's not exactly, that's an approximation, and that's what this is for right here. So let's work with the numbers first, and then let's see if we'll work our way into some pieces here. Okay. Okay. Just let's get used to the math behind it here, and then we'll get to the other things here. So exercise 1 or example 1, however you want to do it here. Here's what we have. Let's say this. This is a good one to sort of see. If you know that f of 3 is equal to 2, you also know the derivative at 3 is equal to 5. Estimate for me f of 3.2. So notice you have no structure here. You just have a dot points that you know of, right? You have a single dot at 3, you know, to be 2. And then you have the instantaneous rate of change at 3. So all we got to do, really just plug into this little formula here. And so we're going to approximate A plus H. We're going to approximate it by H times the derivative at A plus F of A. So the only thing we need to do is really just get this little H value here. H value, tell me if you guys agree. We're going to go from 3.2 back down to 3, so our H value is 0.2. That's how far we are from the value that we know. So f of 3.2, if you want to kind of break it up, you can even break it up if you like, so it'll look like A plus H, if you want to do it that way here. So there's your A, there's your H value. So H value is 0.2. The derivative exactly at I guess I can put the derivatives here plus the f of 3 value itself here. So 0.2 times, what is that, 5, right? Plus 3, oh, plus 2, sorry. And right there. And so let me sketch a little graph here, even though it's not much of a graph here. 1, 2, 3, 1, 2. I got a dot here. And then I have no instantaneous rate of change. It's going up pretty fast, going up to 5 here. So at 2.3, I want to know that approximation at 3.2. All right, answer is just 3, yeah. Easy enough. It's just 1 plus 2. So if that's the case, I have 3 here, and actually that went pretty high. It went all the way up here. That's at least my estimation. So I'm not sure what this graph looks like even, if it's curving up even faster or if it's curving up not as fast, but at least my approximation for 3.2 I get myself is 3. So I'm not sure if the graph goes like this. It's curving a lot faster up like this, but my graph is pretty cool. At 3.2, I at least get this dot there, which is pretty close to the graph. Maybe the graph goes up to maybe like 3.1 or 3.4 or 3.002. That's fine, but at least I get a quick, excellent approximation. And notice not much algebra, not much calculus work to be had. We just plug in numbers. That's it. It's a little crunching machine. That's kind of what we're looking at. Okay. There it is. We're looking for approximations. That's kind of what we're looking at. And I'm going to kind of jump around. That was just the math behind this little average rate of change and instantaneous rate of change. We'll use it in just a bit here, but let's do this here. Let's jump to a physics problem. So motion along a line. And in mathematics, this is kind of what we think about. We think about motion of something along a line. So first things first, let's get some symbols here. Again, this is an application section, which I kind of love. I love these application sections interspersed between here. And then we have a whole chapter on application sections, which will be even more. I like the theory of it too. This is cool. I like both. I guess that's why I'm a math teacher. So let's go with it. Some notation for physics. S of t, which is position. And the t is going to be in terms of time always, right? So whenever we talk about S, you say S of t, you're talking about position, how high it is, how low it is. And then we go to the next one here. which we talked about last time here. We can figure out velocity by taking the derivative of position, and that's going to give us velocity here. Okay, velocity and speed are related, but speed is really the absolute value of velocity. So we don't care which direction you're going. With velocity, we do care which direction you're going. And normally in mathematics, we think about either going to the right or to the left. That's kind of what we're looking at, or going up or going down. So all right, and the last one here, acceleration A of t is the derivative of velocity, or it's actually the second derivative. Notice I put a little 2 notches there. It's the second derivative of position. And we call that acceleration. Okay. So Eli, I'm going to bug you a little bit here. Did you guys do a lot of work with position, velocity, acceleration in physics? Yes, kind of, sort of?
A lot.
A lot, okay, okay, cool, good. Okay, so we're going to get the calculus version of it just a little bit here. And calculus probably a little bit more refined because we at this point we're like, okay, we want to get the equation for it. We want to figure out this. So there's a lot more cleaner in the examples in calculus than they really are in life here. So here it is. How about this one? A ball is dropped from 64 feet high. And so after looking at the ball dropping in terms of time, here's what we have. We have this little ball right over here at 64 feet high. And in terms of time, here's what happens. I let go of the ball and it goes, and then it hits. And we look at it and it's exactly 2 seconds. Whoa. 2 seconds to hit the ground. All right. And if we're going to take a look at this here, here's what we really want to do in calculus here. We want to make a model of it. And once we make a model of it, we want to make a formula for it here. So here's my little formula that I've made. Of course, it's very nice and clean. Negative 16t squared plus 64. That's my position formula for this guy. Interestingly enough here, I mean, when I got out of school, I think I had maybe like 2 or 3 years of teaching underneath me. I went to a job fair, and NASA was there because, was it NASA? Oh, the military was there, yeah. A recruit, it's a job fair. And so just for the fun of it, I went to the booth there and I interviewed with them because you pretty much just bring your resume, you interview. And it was to work in the Mojave Desert. And it was pretty much just to look at graphs of rockets and look at their speed, acceleration, velocity, position, and tell me what's happening. That's pretty much the crux of the job. And you launch a rocket, you have all these visuals of it. You have 3 different or 4 different, of course, you have thrust, right? You have all these different monitors of everything, and that's it. Your job is to interpret the graph. And why did it fail? And why did it go down? Why did it not do what it's supposed to do? And so that's kind of like the thing here. There it is. It's just, you tell us what's happening here. So 2 things here. We're going to look at what's the instantaneous. So let's calculus question. Here it is. How fast is this guy going to hit the ground? That's question. What is the, so A, what is the instantaneous velocity when the ball hits the ground? How fast is it going? Sorry, Eli, go ahead. Can you speak just a little louder? For some reason, the microphone is not catching.
Can I use the physics equation instead of the calculus?
Oh, yeah. Tell me the physics equation. Go for it.
Well, the velocity final squared is equal to the velocity initial squared plus 2 acceleration times the distance.
Acceleration.
Times distance.
Mm-hmm. Okay, perfect. So velocity, initial velocity squared would be 0 because I let go of the ball, right?
Yeah, so 0 is the initial velocity. Acceleration is just gravity because you dropped it, so it would just be 9.81 meters per second is the acceleration.
Uh-huh.
54.
And the distance would be just 64, right?
Yes.
Okay. That's awesome. Okay. Thank you so much. That totally adds to the class. Okay. You get that one. And then I'm going to go back to get this little one right here. So this is, can you give me the answer for it? So 9.81 times 64.
It's 627, and you take the square root of that because it's velocity final squared, and it's 25.1.
About 25, yeah?
Yeah.
Okay, and I think the difference is this is meters per second here, and we're looking at feet. So it'll be, let's leave that just for a little bit. I want to make sure that it connects together here. Okay, let's do the calculus way. Let's see what we got. The nice calculus way here. We take our function, and all we do is we have to take a derivative of it, because once we take derivative of it, we get back down to velocity. So how about negative 32 t squared, or sorry, just t, right? That's a plus 0. Everybody good there? I moved from position down to velocity. Okay, and then I know when it hits the ground, it hits the ground at exactly 2 seconds, right? Exactly at 2. According to this one, right? According to this ball dropping. And so what we want to do is we want to plug in the 2 now. And so at this point, okay, let's go for it here. So this is the non-calculus equation here. Here's the nice, pretty calculus equation. Is 64 meters per second same thing as 25 meters per second, same thing as 64 feet per second? Anybody got a conversion between feet and second in meters?
Yeah. 64 feet a second to meters per second?
I guess so, yeah. So 64 feet going into meters. Uh-huh.
Oh, yeah. 64 feet per meter is 19.5.
Feet in meters. Sorry, say that again, just a little louder here, Eli.
19.5 meters.
Is that the conversion between the two?
Yeah, 64 feet is 19.5 meters.
Oh, okay. 19.9 meters?
0.5.
0.5. Thank you. Okay, we have a little disparity, guys. Look at that, because the 64 feet are going to cancel each other out. So according to this one, and you guys tell me if I did the math correctly here, guys, I get going from calculus into the non-calculus version, I got myself 19.5 meters per second. True?
Yeah.
Yeah, so there's a disparity between.
Well, because the physics one, if you converted, you can't really plug feet into it. So I converted it to meters first, and then plugged it in the physics equation, and it worked.
Sorry, Eli, say that just a little slower and a little louder because I'm having my microphone is up.
Well, for the physics equation, you plug feet into it, but you need to convert it to meters first. So I converted it to meters and plugged it in, and then I got like 14. So closer.
Uh-huh. Interesting. Okay. I'm going to leave that to grapple with for a little while. So which one's, you kind of think about which one is off here. But give me the numbers that you plugged in for if you did it in terms of feet.
Which the physics equation?
Yeah, uh-huh.
Well, you can't really plug feet into it because we have the acceleration as meters.
Got it. Okay. Uh-huh. Gotcha. Okay. I'm going to leave that for a little while, just sort of see what comes of it here. Eli, but you tell me what you did initially. You said you converted the formula from feet into meters?
I just converted 64 feet to meters.
Oh, like right over here, right? That one?
Yeah. Well, I was just trying to plug it into the equation.
Yes, yes. Sorry. Uh-huh, yeah. Like right over here, right? The distance should be in meters, not, right? Is that what you're saying? Okay, yes. Okay, this one right here. You put in 19.5, right?
Yeah.
Gotcha. When you came out of that, that gave you 14-ish.
Yeah.
Gotcha. Okay, yeah. I just want to make sure that I understand what you're saying here. So that's what we have here. But then when you convert it in here, it's still going to be off. Off by 5.5, right? A little closer. Yeah, right? Okay. Gotcha.
I would say the calculus one is probably.
Say again a little louder.
I would probably assume that the calculus one is more accurate. But
Yeah, and I would say the calculus one is not so much more accurate, but more theoretical and more of exactly how this should happen, sort of thing. Part of it is, negative 16 feet per second. And I'm not sure if that entails a little bit of air resistance as well, right? Because there's that little piece there that needs to be accounted for. So that's cool. Okay, I'm going to think about that. My little vacation problem right there for me to consider. Okay, we're jamming. Are we good with that one here? So that's the instantaneous rate of change. And that's what we normally look at in calculus here. It's that little, what's happening right at that moment, right at the moment it hits the ground, or right at the moment that it's 25 feet high, right? It's that little fast movement of things here. Let's go with the next piece. It's a little bit of a same thing, yet a little bit different. Actually, no, we should do the average rate. Average rate of change for this one. Let's do B here. So that was the instantaneous rate of change. How about the average? And remember, with average, all we're going to do is we're going to divide by the length of it, right? So this was negative 64 feet per second. We're going to divide it by the 2 seconds that it was in the air. And so in this case, negative 32 feet per second is the average that it was flowing. Now, notice that the average is way different from what's happening actually with the ball, right? Because the ball, when you release the ball, it slowly starts going down, right? And it gets faster and faster and faster and faster, right? When you take average, it doesn't tell you much because it just tells you how fast, right, it's going from beginning to end, right? And averages could be as skewed as we learned last time with the blood concentration. So, okay, there it is. So instantaneous, I think the book really wants you to understand the difference between instantaneous and average. There's your two that you have. Okay. Are we good there with those? Let's jump to a little bit more abstract. This one right here, it's something called position and velocity. This is the way we think about it in terms of calculus. And again, maybe slightly different than what we think about it in physics. And so we think of a object moving on a grid system, and system usually is like this. It starts off at one end, 0, and then this always in terms of time. And so maybe a good example, it starts off like right here. It goes off to the right for a certain amount of time. It changes direction. It goes backwards a little bit, and then it goes forward. You know, something like that. That's the way we sort of think about motion. It's a right and left movement. And then obviously you say, Mr. Ng, our world does not go just in left and right. Absolutely. And then we have to go into three-dimensional mathematics or calculus. And then that's when we get the other dimensions here. And so for now, we're just going to move a dot from one side to the other here. So position and velocity, let's go for it here. So position of a particle. Oh, this should be exercise number 3, I believe. Is that right? All right, position of a particle. Here it is given by this. S of t, of course, position has to be s, right? T cubed minus 9t squared plus 24t plus 4. Okay, the only condition is that t is greater than or equal to 0, obviously, because you can't go back in time unless you're Michael J. Fox and you go back to the future. No reference to Back to the Future? Okay, let's go for it here. So there's my equation for a particle, again, going to the positive side, which is to the right, or the negative side, which is left. And so we're going to actually eventually graph this. So what we want to do is we want to find v of t. Let's find our velocity function here. Then I want to know what times is the particle at rest. What times is the particle at rest? When is it moving right or left? And D. Sketch. Sketch the graph. Okay, we're good there. So find the velocity function here. We're going to figure out when is this particle at rest, which means not so much rest, when is it changing direction? When did it stop moving to the left, starts moving to the right, or starts moving to the right, going to the left? Sorry, not of left, sorry. The C version should be right or left. All right, so first one, all yours for the first one. I think you guys can do that here. Can you find me the velocity function? And A and B are very closely related right there, because once you know the velocity function, you're trying to figure out when is this guy at rest, which means velocity is going to be equal to 0, or the times where the velocity is equal to 0. Let's go with it here. So A, it's going to be V of t is equal to, I think 3t squared. Is that right? Minus 18, you said, t? And I got the last part is 24. Everybody agreed there? Cool. So we grab that, and then we set it equal to 0 to solve. For the second part, sorry, boom. There's V of t. For the second part is we just set that equal to 0. I think I'm going to factor out a 3 first, because 3 is kind of bugging me inside there here, because that's going to go into all of them. Okay, and now I think I can factor nicely. Minus 2, minus 4. I'll grab the other one here. So solving it here, I got it. It's x equals to 2 and 4. So the particle is at rest at t is equal to 2 and t is equal to 4. And I'm going to put over here, I know it says rest. The particle is at rest, but really we should think about is changing direction. That's what we should think about at rest. Okay, boom, boom, boom. So C, let's jam with that here. So particles at rest there. So the change of direction happens at time is equal to 2 and time is equal to 4. Yeah, in terms of seconds, if we want to just kind of think in terms of seconds here. So do you guys remember back in Algebra 2, do you guys remember when we were talking about, is it above the x-axis or below the x-axis? Remember how we had these little points right here? So 0 has to be a starting point for us, right? But we have 2 is a problem, 4 is a problem. And remember how we used to either put a plus or minus between these guys? We'd say, oh, that's plus. That means and you got a minus. You had little test points between the two. You guys remember that sometime ever?
I don't think we did that. I don't think I've ever seen that.
Oh, wow. Okay. Okay. Let's see. I'm thinking about that's when we did rational functions, I believe. Huh. Okay. So never mind. I'm not going to refer back to that. Let's go back to this then. So the question is this: in the interim, so notice from 2 to 0, from 0 to 2, right? We have that little direction. We just need to figure out during this time, is this guy going to the right or to the left? And then we know it changes. We could possibly change direction at 2. We don't know. So we're going to have to test a little piece from 2 to 4. And then we're going to have to test after 4. And the question is it going to the right or to the left? That's what we have. So really we're testing is this, is the velocity positive or negative in the interim between 0 and 2? And so we test. We could put a little X mark right here for 1. That'd be fine. But really we're testing this. We're testing V of 1. And really, we don't even care what the number is. We care about what the sign is right here. And so this is 3, this is minus 18, that's 24. Are we okay with positive number? Let's see, is that what, 6? That's 9, is that 9?
Yeah.
Okay, 9, but I don't even care what the number is. I just care about the fact that it's positive. So from 0 to 2, this thing is going off to the right-hand side. It's going in a positive direction. So now we got to pick a little guy between 2 and 4. 3 is a good one. So all yours to figure out 3 as a test point, and then maybe let's pick 5 as another test point. You could pick 7, 10, who cares, right? You could pick anything above 4. So let's go with it, picking 3. So question is, what is that, positive or negative?
-3.
Sorry, Eli, -8 you said?
-3.
-3, perfect. Okay, so I just care about the symbol. I know it's going to go to the left side, and V of 5. If you guys can punch that in, V of 5.
+9.
+9, and that's all I care about there. And so and we talked about this as being a particle moving, right? And that's true. We do have some sense of movement, right? You could also think of this as thrusters blasting, right? At a certain duration, the thrust of it is increasing, right? From 2 to 4, the thrust of it is decreasing for a while for some reason, and then it goes on higher again, right? There's that little piece there. So for C, I think we got that little piece there now. So it is moving to the right from 0, starting at 0. So I should put a bracket here. 0 to 2. And whenever we talk about the endpoint of it, we don't ever include the endpoint because at the endpoint, it's at rest. It's changing direction at that point. And then anything after 2, nope, anything. Sorry. Right, 4, is that right? 4 to infinity. There it is. All right, it's moving to the left. That little gap from 2 to 4. Okay, are we good there so far? So right movement and left movement. You can think of something getting larger, something getting smaller, if you want to think about it that way as well. Something increasing for a while, something decreasing for a while. All those things, any kind of rate of change kind of ideas here. Okay, good. I think we're almost ready to graph this guy. So let's jump to.
But how are there only 2 directions?
Sure, yeah. So we talk about particle movement, right? So until we get to third dimensional calculus, which is calculus 3, then we start putting into multivariable. So then it's kind of cool too, because we think about different fields inside, field directions. You can almost think of almost like the wind, right? If you say, okay, what's the wind all around slow, right? And we think, okay, at this field, the wind direction is moving this way. At this one, it's this way. And this one, it could be a higher magnitude than the other one. So that's when it gets into a whole complex sort of piece there. Okay, C is good. Eli, are we good with that?
Yeah.
Good question. That always comes up in this section here. Okay, so I think we're ready to graph this guy. So D, the only thing we need now is the starting position. What's our starting position? What is S of 0?
getting for others, giving.
Everybody agreed with 24?
I agree with that.
Everybody agreed with 24 S sub 0?
Yeah.
Yes, okay. So now the other things that we got to think about is anytime we had a change of direction. So let's do that here. We had a change of direction at 2 and 4, but we're going to plug it into the position function because that's eventually what we want to know. We want to know what the position was when this turned. So S of 2 I need to know, and S of 4 I need to know. Yeah, S of 2 and S of 4.
No, that's not what we're asking.
Oh, it's 24T plus 4, not plus 24.
Oh, plus 4. Gotcha. Okay.
Then S of 0 here.
S of 0. Thank you so much. Why did I put a 2 in there? I have no idea. Okay, 4, which is the beginning value is going to be 4. Perfect. S of 2, please. Anybody?
It did. Look at it. You turn it on. Your batteries are low. Recommend taking batteries. Ignore it. Start going. You weren't even watching.
I was just doing the math in my calculator.
That is not. Oh, never mind.
For S of 4, I got 20.
S of 4 is 20. Okay, I'm going to go with it here. Boom. And then I need S of 2.
Plus 4. 8.
For S of 2, 24.
24. Okay, I'm going to go with it here. Cool. I think we're ready to graph this guy. Okay, so let's go from now into position here. So we got the time factor all done. So now we're going to go to the position factor. So let's go with 0 here. And I think we need to go at least up to 24 on the right-hand side, right? We could put a 0. Let me do this here. Let me put, since we don't go to the negative side as much, we're going to go like this. How about this? Let's start off 0 being all the way down here. 1, 2, 3, 4, 5, 6. That'll be good. And so 24 would be about right here. And these guys are every 6 notches. Two, 3, 4, 5, 6. 6 times 4 is, so that's 20 here. Will that work? 4, 8. Oh, no, that's not going to work. Why am I missing it here?
Wait, how many numbers are in
1, 2, 3, 4, 5. Oh, I'm off by 1. There you go. Sorry. 6 should be about right here. Is that right? Boom, 24. Because I'm trying to capture the 24 and the 20 and the 4. That's all. So I'm thinking in terms of 4 each time. We're good there? Sorry, off by 1. So how about this? 4, 8. Let me count it just to make sure I get it right. Yes. Okay, I got it right. Boom, 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 boom. Don't need to go into the negatives because it never went into the negatives. This particle. All right. And at first, this is kind of weird because it's the first time you see a graph like this. This is us trying to figure out how to do movement and position and velocity at the same time when we do this. So here it is. We put a little dot right there. And we say time is equal to 0 right there. but our position is at 4. Good. And we really don't, again, it's not a 3-dimensional movement. It's just a 2-dimensional movement, right? But a 2-dimensional movement in terms of time. And so what we say is all the turns that happen, we're gonna make sure that we get to those here. So we're gonna go straight on through here. And we'll do a little turn here at 24. And we label that as time is equal to 2 seconds. And then what we do is we turn around, understanding that it does need to turn around. And then we put another dot right over here at 24, a little bit higher than the previous dot here. And this is going to be t is equal to 4. That's when it turned the other way. Is that right? And then from then on out, it never turned back. So then we know it's going to go off to the right. Again, seeing this for the first time is a little bit weird because first of all, we're used to doing functions on a graph, right? And this is totally not a function graph. And we're trying to combine time and position together into one graph.
So the graphs move up instead of like left to right on a normal graph?
Correct, yeah. And the time, as you think of time, time moves up through it, but time moves up only at the times it changes direction. Right? It's not like a continuous time value going up the y value. Okay, I'm going to leave it there, let you guys play with it, okay? I know in the previous textbook we used this, it was introduced a lot later in the course in derivatives. Almost like that a little bit better because this kind of throws students for a loop sometimes. Okay, let's jam. Let's see, we've got 10 minutes left here. Oh no, hold on. Are we, yeah, 45 after, right? Okay, let's see if we can get through the 2 other ones here. So that's that one, that's 3, right? This is 4. 4, let's do real quick here. Population growth should be pretty easy, and then the economics one might be a little bit more complicated here. So let's do this here. Population of a city doubles every 5 years. So population of a city doubles every 5 years. Current population equals 10,000 people. All right, what will be the approximate population all right, 2 years from now. 2 years from now. So notice there is no formula. There's no fun little function that tells us this. That's all we get to go by. And so with that, notice we're going to approximate it, right? And so let's go back to our little formula. I think the formula is approximately, right? H times F of A plus F of A. Okay, I think that's our little formula. Okay, our little thing is we got to get, let's see, do we know what we need to know? Yeah, H is going to be 2 years, right? Because it's 2 years from here. H is 2. I think I got that one. Oh, this one's easy too here. This is 10,000. So let's see, do we want to put everything in terms of Yeah, let's go with this would be what, 10,000? There's 10,000 currently, right?
Yeah.
Okay, our little thing is we don't know what f of prime of a is. That's our little issue here. And so we just know it doubles every 5 years. So how about this? We're going to go with this right here. So f of a value is technically 0, is that right? And we're trying to go from here to the next level. So we know it doubles every 5 years. So see if this makes sense. I'm going to go with 5 years later, subtracting our current. So 5 minus 0, if it's going to double. So then on top, I have 10,000 is my current value. And if it doubles, what's the double? Double is going to be 20,000 people. Is that right? That's what I have here. So 20 minus 10 is 10,000 divided by 5. And I'm looking at my approximate instantaneous value is 2,000 per year, right? Kind of like an average. Okay, talk to me if this makes sense. So we got a little slope value here. So now we can plug it in. This is going to be 2,000 right over here plus that one right there. So 2 times 2,000 plus another 10,000. I'm looking at 4,000 plus 10,000. We should have about 14,000 in 2 years. And so this is so relevant, so important here, because when you judge population growth here, I mean, in California, even in politics, we think about, where we're going to get more energy from, right? And should we go wind, solar? I mean, there's a whole push for solar energy, right? And so then the question is coming up nowadays, should we go into nuclear power? Would that be the better way to go? So all these things, but it's why? It's because of population growth. And at the same time, you think also water capacity, water recycling efforts. I mean, all those things come into this whole concept of, can you judge population? Can you approximate population growth with it? Anyways, are we good there?
Yeah.
Okay, we got what, 4.5 minutes left here on my clock here. I think we can make the next one here. Should we make the next one? Let me take a look at your homework, actually. Let me see just real quick if we find the velocity question, price question. Yeah, we should, because we have some price questions. Okay, 4 minutes left. Let's jam with the exercise number 5. Just introduce you guys, maybe just do the first part of it here. So marginal cost. So we have this guy here, C of X is cost, usually in business and economics here. And then we have something called MC of X. MC of X is marginal cost. And it's this right here, the derivative of cost itself. In fact, even if we get through all the equations here, I think it will set you guys up for the homework here. So there's marginal cost, MC, or just derivative of C. And then same thing happens over here. So you have R of X is revenue. Right, and then we have in business, we have M of X, which is the derivative of R of X. Okay, yeah, and in fact, you know what? Even I give you guys the equations, I think you guys would be okay with the equation itself. So we have that one right there. And then in business, again, we have profit. What is profit? Profit is always revenue. How much did you take in? Subtract the cost that it take you. to bring in those profits here. And we have marginal profits, which is going to be the derivative of profits. And again, it's this right here. Let me give you both. This guy, oh, sorry, revenue first, RM minus marginal cost, or the derivative of revenue minus the derivative of cost. All right, where does this come in? You know, and I'm going to stop there because we're running out of time here. So quick story here is GM Motors. 15 or 12 years ago here, they were bankrupt because their marginal cost and their profits, their marginal profits were negative. They were paying out for retirees that have retired already. They were paying out for the factory workers, a lease on the factory. So they eventually were looking at this and it was actually negative. And so they said, okay, we're done. We are going into bankruptcy at that point because we can't keep up with expenses on the marginal level. And so the government gave them a whole bunch of money. What they had to do is the new CEO came in and they did have to cap retirement. Retirement wages. They had to cap those. And all the workers got slashed in their wages as well. But eventually that marginal profit started to become positive again. And again, very important to see that, especially in the long term. Like, what's the company doing long term? Okay, I'm going to stop there. At least you can have the formulas to do the economics problem for homework. All right, you guys have a great vacation. I'll see you guys next year. Whew, that'd be fun.
I have a question, Mr. Review.
Yeah.
Did our grades on our last test get implemented on midterm?
No, thank you so much. I'm going to be grading this week, this week, and catching up on all grades. So you guys should see some. You guys should see your Google Classroom grade change. If you have any questions on it, please email me on it. Okay.
Okay.
Otherwise, I'm going to try to finish by Friday everything, just so it's all set, and then I'm going to start my vacation.
Thank you.
Cool. Okay. Absolutely. And if you guys don't forget to spray down the chairs and the desks, please. Cool. All right. You guys, see you guys later. See you guys next year. Enjoy your vacation.
You too.
Thanks.
This is going to do really well on the derivative test.